G'day everyone, welcome to Lubrication Experts. And today I've got a really pretty special topic. I say that every week, but this one in particular I think is something which will be really interesting to the audience. We're going to be talking ultrasound and ultrasound mainly as a condition monitoring tool as it relates to lubrication, but we might branch out a little bit beyond that. And there is probably no better person to talk about ultrasound as a condition monitoring tool than my guest, Allan Rienstra. So he is the CEO of SDT Ultrasound Solutions. So if you wanted a person who's got more experience and more know-how in this kind of field, not sure that we could really find anyone else. So Allan, thank you so much for joining us.
Well, that's quite a compliment. I'll take that. And we'll just clarify, we're going to talk about ultrasound. We're not going to talk ultrasonically because then nobody will be able to hear us.
Yeah. No, good point. Good point. Unless there's any bats in the audience. So, and that kind of actually leads into the first question, right? Which is basically like, what is ultrasound? So you've already made a distinction between kind of what you might call regular sound and ultrasound. And people are probably also familiar with regular light versus ultraviolet light. So can you please maybe distinguish between the two, and then also describe like how that manifests in something like an industrial environment, like what kind of things give off regular noise versus ultrasonic kind of noise.
Sure. So just to begin with, what is ultrasound? We can look at it and say, well, ultrasound is a classification of sound. There's three classifications of sound. There's infrasound, which is low frequency sounds that we can't hear. That's great for bats, and it's great for, not for bats, sorry, for whales and elephants, and it's great for seismic sensors to find earthquakes and things. Then there's audible sound, like our voices or all that noise that we hear in the plant when we're working, and then ultrasound. And ultrasound is above. So, a non-technical description would be to say ultrasound is any sound that's above the human range of hearing. I say non-technical because everybody has a different threshold for hearing. Mine used to be 17, 18 kilohertz. Now it's about 11 kilohertz. And that's just due to, industrial exposure and age. Those three different classifications of sound, well, we're really interested in ultrasound. The technical definition or the scientific definition would be any sound frequency or sound pressure wave that has a repetition frequency above 20,000 hertz or 20 kilohertz. Now, we also refer to ultrasound as a testing technique. So, if you've ever had a sports injury and you've gone to have some soft tissue repair, the doctor will perform, or your therapist will perform, medical ultrasound on that to relieve swelling. If you've ever been pregnant, then you'll have had medical imaging, an ultrasound for medical imaging. And these are all using really high frequencies to diagnose and to treat tissue. We also talk about ultrasound in the industrial sense as a condition monitoring technique. And so if you look at the core technologies for ultrasound, where you have thermography, vibration analysis, motor circuit testing, ultrasound and oil analysis. Let's just stop it at those five, because there are more, but those are kind of the five. If you look at each one of those, each one of them kind of appeals to a sense, right? So, oil analysis, well, that's kind of a touch. Vibration analysis is feel. Thermography is touch again, it's heat. Oil or ultrasound is, hearing. And if you go back to caveman days, well, I think if your chances of surviving against a saber-toothed tiger would be best with your hearing sense, because you can hear them sneaking up behind you. That's really so that technique takes us into industrial ultrasound, where it really gives us, it's a technique that gives us that best opportunity to hear and to listen for and detect asset faults.
Yeah, interesting. So, we've mentioned very briefly that machines kind of give off some kind of ultrasound, right? In a sense. So what kind of ultrasonic signatures would come from typical machines. So, I mean, for us, it's mostly rotating equipment assets, right? Most of the time when we're thinking kind of like lubrication, but I guess it could be any machine really.
Yeah. Yeah. So the reason that we perform condition monitoring is so that we can, anticipate. I shy away from the word predict, even though we talk about predictive maintenance. Since 80 or 90% of failures are random, that you can't really predict it no matter how much data you have. But so let's just say we can use these technologies to anticipate that something's going to fail. Well, that's great. So you have to do a failure modes and effects analysis on every asset to know what are the symptoms of failure. And for ultrasound, the 3 symptoms of failure that we can detect better than probably any technology are friction, impacting, and turbulent flow. So if you take the first letter of each of those, it spells fit, and we want fit assets: friction, impacting, and turbulence. That's really what we're listening for, and that's what gives us the golden nuggets of information so we can anticipate these failures.
Yeah, that's interesting because, I mean, all 3 of those, also give up what you might call audible noise, right? That's in the sort of the range of human hearing. And I think everyone's probably familiar with the screwdriver test. Right? There's always some person on site who has developed, the capacity to listen to bearings.
Yes.
And I think all of us have probably experienced it sometime walking past a hydraulic circuit that is cavitating, and you can hear it. Friction. We'd probably all run past a bearing that hasn't been greased in a little while, and you can hear it, or turbulent flowing lines. So what makes the ultrasonic signature different from the audible noise?
It's the characteristics of the higher frequencies. So again, if I go back to infrasound, audible sound, and ultrasound, as we go higher in the frequency range, there's certain characteristics that change. But the overriding one is, as we go higher in the frequency range, that wavelength becomes, the period of that wavelength becomes shorter and shorter and shorter. And because it's got a shorter wavelength, it also has lower energy. Lower energy meaning, for an ultrasound wave or any sound pressure wave to travel from source to sensor, it needs a medium. It needs a molecular structure. It can't travel through a vacuum. So to get from my mouth to my speakers, or my mouth to your ears in a conversation, we need those air molecules to transmit the energy. As we go higher in the frequency range, because the energy is lower, the sound tends to travel a shorter distance before it gets attenuated or absorbed by its medium. That medium doesn't have to be air either. It can be this desk, it could be wood, it could be steel, it could be water, it can be anything with a molecular structure. The point being with ultrasound is that because it's low energy, it doesn't spread out and it doesn't travel a far distance. You'd think that those are disadvantages for us, but they're actually very advantageous for us. As you mentioned earlier, the high noise in our work environments, and we wear hearing protection to protect ourselves against that. But if we're trying to find a compressed air leak or an electrical fault, or even just listening to friction from a shaft coupling, those assets are transmitting ultrasonic signals through the air. But if we were listening to them at an audible level, we wouldn't be able to distinguish where they're coming from, because they'd be traveling in 360 degrees, they'd be bouncing off the walls. Well, what an ultrasonic detector or an ultrasonic data collector does is it uses a high filter to cut off everything below 38 kilohertz. So if it's below 38 kilohertz, the instrument's completely deaf to it. And if it's above 42 kilohertz, it's completely deaf to it. So we've narrowed down to this really small band of ultrasound where all of this friction, impacting, and turbulence is occurring. We've eliminated everything else so we can just hear exactly what it is we want to hear without being interfered by other things. I hope that's clear.
Yeah, that's really interesting. So I think, for most of us that are listening, um, 95% of the time, if we've had any interaction with ultrasonic sensors or ultrasound tools in the field, probably really one of two things. We've probably seen NDT inspections. It's probably, ultrasonic testing that way. And that is more, I guess, kind of in the vein of the ultrasounds that you mentioned for like pregnancy scans and stuff.
It's really similar.
Yeah, we are emitting ultrasonic waves and kind of looking at the reflectors, right? Versus the kind of ultrasound that we're talking about in a condition monitoring environment where we're not giving off ultrasonics, we're just detecting. Now, in most circumstances, I think the other way that people have seen it would be for ultrasound regreasing, and that's
Yeah.
really commonly employed tool in the field, especially I find in terms of getting a technician up to speed on getting just the right amount of grease, it's probably the easiest way that I've seen so far. So maybe could you please just let us give us a bit of a flavor for the technicalities of how that's done? Because most people would have just seen kind of basically the decibel meter and what they're just looking for is the number go down, right? It's really what they're looking for.
Right.
But maybe you can get into a few more of the specifics of like what's going on inside the bearing as we are applying grease, which changes that sort of sound signature.
Good. That's a good way to tackle it. I always start this discussion with a really high level question, and that's why do we lubricate? You're the lubrication expert, so you can probably answer that one. But we get all kinds of different answers to that question when we ask it. But the biggest one is to create separation between the components, right? We don't want the balls touching the race. We don't want the cage touching the balls. So we create that thin microfilm of separation between all of the rolling elements of the bearing. And that only happens when, first of all, a tribologist specifies the right lubrication for the application. But then when the right quantity of grease has been put into the bearing so that it can form that little wedge of grease. I always like to compare it to that yellow sponge on your kitchen sink, yeah, where the sponge is the thickener, and when you squeeze it, the water and the soap that comes out is your additives and your lubricant, or your base oil. And so it's that kinetic energy of the bearing spinning that squeezes just the right amount of lubricant out to form that little wedge. And when that wedge fails, or when that greasing mechanism or lubricating mechanism fails, we have an increase in friction. Simple. So the bigger answer to the question is, why do we grease? So to control friction and I suppose keep contaminants and things out as well. But there's no better technology to listen or to detect live changes in the friction in the bearing. So what we're doing, there's a whole host of different ultrasound technologies out there. So from low cost, low level, to what we call listen-only devices. A listen-only device could be that screwdriver that you talked about, or it could be an ultrasonic probe that's just connected to a circuit that gives you an audible signal only. Then you can get into digital decibel metering devices like our lube checker, for example. And our lube checker, it's a listen only device, but it's not listen only. It also gives you feedback. It gives you that decibel level. So as you're listening to the bearing, and as you inject grease into the bearing, you can see the decibel level drop, and you can hear the friction improve. So that's a quantitative re-greasing of the bearing. Now, the upside to that instrument, or that tool, that digital decibel tool, is that it's a single point set of instructions. It doesn't take a really high competence level to use it. You can pretty much give it to a lube tech and say, Now you're going to start listening as you inject grease. Oh, okay, no problem. And it's really the first time they use it, it's like the lights come on. Wow, that really works. Then we go one step further, which is kind of a higher level device, such as our Lube Expert. And our Lube Expert has the same listen only ability, the digital decibel metering, but then it also has a smart brain inside of it, an algorithm. And that algorithm is continuously comparing previous injections and the effect of those injections of grease. And then it's giving you step-by-step guidance with every shot that you give from the grease gun. So in order for that to work, you have to set up a database. That database has to be all of the bearings that you want to grease. It has to include the bearing numbers. We need to know the dimensions of the bearing and which type, whether it's a side fed or an annular fed bearing. We need to know the RPM. We also keep a database of your actual grease gun. So we know if you're greasing a 6613, I'm just throwing a number out there, bearing, we know the capacity of that bearing. So now we're going to match the capacity of the grease gun to that bearing. So if we have to add 50 grams of grease, well, we don't want a grease gun that is 1 gram per injection. You want one that's 10 grams per injection. So you're not sitting there getting carpal tunnel syndrome while you're lubricating. But so that algorithm and all of that information that we feed into our database, now you have you essentially have step-by-step instructions on the screen. Do this, wait. Did it make it better? Did it make it worse? Okay, now give it a little bit more grease and a little bit more grease until you reach that perfect plateau. Now, the other cool thing about the Lube Expert is that it does something that the lube technician doesn't even realize he's doing, and that is it's collecting data about the condition of the bearing. So while he's greasing the bearing and getting that feedback, the Lube Expert is storing a time waveform and a spectrum on the bearing. So when she uploads that data from her task back into the software, the manager's now going to not only see that the bearing was lubricated perfectly, but they also see a time waveform of the bearing, and they can see if there's any fault frequencies occurring in the bearing. So that's, I've kind of taken you from the low end right to the top end.
Okay, so there's some interesting things in that. I think one of which maybe people aren't aware of is that you can get the type signature out of an ultrasonic greasing tool. There are also other ultrasonic devices that will kind of, you're just doing an inspection, that will do a similar thing. I guess what we are able to then do on the back end, through, I'm assuming, some kind of FFT analysis, would be to effectively do a very similar type of analysis to what you would see with VA, vibration analysis.
Exactly.
In terms of actual fault detection, and root cause failure analysis, that sort of stuff. Is that kind of like where you're getting to? And maybe is there like software that is going to help us with that detection, or is it something that just needs to be learnt to do manually?
Yeah, so to answer that question, let me just start by making a statement, and that is that the higher the frequency of your condition monitoring, the sooner you're going to detect problems. So if we're only relying on vibration analysis, which is typically 10 kilohertz or lower, you're going to find problems, but you're going to find them later in the P to F curve. The higher you go in the frequency, the earlier the indication of a conditional change. And that's what makes that's why we say ultrasound is kind of your first line of defense against asset failures. So, that's part of it. So what we had with vibration analysis is we have a technology that we say ultrasound condition monitoring, vibration analysis. So with ultrasound, we're monitoring condition. With vibration, we're going deeper and saying, well, what's the root cause of the problem? What we've done at SDT is we've added in a database of bearings. It's about 50,000 bearing references have been added into our software now. And each of those bearing numbers comes with a unique fault frequency. It's exactly the same tools that vibration analysis has. So we've kind of leveled the playing field. The advantage here now is that with ultrasound, we see that problem much sooner. So if we have a stage 1 or a stage 2 failure in a bearing, we can, which isn't going to get picked up with vibration analysis easily. Now we can plug that in and see if it's an inner race or an outer race failure. So we're doing similar diagnostics with ultrasound, and the data is being collected by your loop tech.
Interesting. So that then brings us into, this is kind of like an age-old discussion of where you apply different condition monitoring tools, right? And everyone's kind of got their favorite. And in my experience, there's nothing which is a panacea, right? Everything has its limitations. So you bring up a good point about the comparison between ultrasound and vibration analysis. So maybe to play devil's advocate, if we were to flip the question around and say, okay, we know that ultrasound's got some kind of limitation. So where would you select vibration analysis over ultrasound as a tool?
So to me, the big difference between vibration analysis and ultrasonic condition monitoring is competency curve. So how long does it take me to get a brand new junior technician trained to be competent at either one of those technologies? And with ultrasound, you can be Cat 2 certified and very capable within 7 months. Versus with vibration analysis, if you want to get to Cat 2 and even Cat 3, we're looking at anywhere between 2 and 7 years. So from an investment point of view, if you're an asset owner and you're investing in human resources to manage these assets, you certainly want to have fast ROI, and 7 months is pretty good ROI. So that's one area. But I mean, if ultrasound was the greatest thing in the world and we didn't need vibration, then why is it still around? Well, vibration is really vital. Anything that I'm saying right now is not to be posed as ultrasound's better than or the best of all of these condition monitoring technologies, because I think all of the condition monitoring technologies are complementary, and there's none that are more complementary than the symbiosis between ultrasound and vibration. Now, so if ultrasound, I like to compare it to the relationship between a doctor and a nurse. If you go to the emergency room, I'm sorry for you that you had to do that, but if you do end up finding yourself at the emergency room, who's the first person you're going to see? It's going to be the triage nurse. And what is the triage nurse going to do? They're going to take your blood pressure. They're going to take your temperature. They're going to ask you, why are you here? And they're doing condition monitoring. They're feeding all of the data onto a chart so that the doctor doesn't have to do it. They're a filter for the physician. I look at ultrasound and vibration the same way. Ultrasound is a condition monitoring filter. If you're taking a Cat 2 or a Cat 3 vibration analysis and sending them out into the plant and say, go find problems, you're mismanaging your resources. You can do that with ultrasound. You can use ultrasound to tell the vibration analyst, these are the 5% that have faults in them. Don't worry about the other 95%. We don't have to look at those. And so what ultrasound does is he makes the vibration analysis much more effective with their time. Where I think vibration analysis exceeds or excels, especially if you get into three-axis sensors and so forth, it's the analysis. It's actually that root cause that you alluded to earlier. That's something that vibration analysis does far better than ultrasound. And then as far as, like balancing a fan or detecting misalignment, those are things best left for vibration analysis, in my opinion.
Yeah, interesting. So I think that's super helpful for people to be able to set up a bit of a framework for how to use kind of ultrasound and VA together. I think from my experience anyway, with some of the maintenance teams that I've worked with, one of the big advantages of ultrasound is, like you said, the learning curve is relatively shallow, steep, quick. is what I'm looking for.
It's quick.
So you can deploy it in the field pretty readily, like your fitters, your greasers, your lubies. They can take on that condition monitoring tool relatively easily, whereas expecting them to become Cat 2 VA is maybe a little bit of a stretch in a lot of circumstances.
Yeah.
And partially that's just because of how quickly some of these job roles move on. Right? You might only have these guys for 2 to 3 years. By the time you invest in sort of training them up, they're gone. And so, I mean, from what I see, at least in a lot of mine sites in Australia, you have a lot of ultrasound technicians, effectively. VA tends to be a little bit more specialized. It'll often be maybe an external consultant that comes in to kind of do that sort of deeper level analysis and that assessment. So I think that seeing those two as the complementary disciplines makes a lot of sense.
Mm-hmm.
Just to expand a little bit, kind of beyond lubricants and lubrication, just a little bit, to give the audience a bit of a taste. Ultrasound and its relation to friction, I think, is being well explained. Where else does ultrasound kind of shine? So you've already got someone that's got an ultrasonic meter in a plant. What else can they go out looking for?
So many things, but so many things that we discovered a long time ago that it was difficult to sit here in front of a camera and a microphone and explain it all. Yeah. So what we do, because there's literally hundreds of different things that you can inspect with it, but if we boil it back down to the sum of its parts, remember what I said, we want FIT assets, and FIT is an acronym for friction, impacting, and turbulence. So you just have to, anytime you're saying, well, what can I use ultrasound for this, or can I use it for that? I always just ask the same question. Well, does the defect that you're looking for produce friction, impacting, or turbulence? And if it does, then it's a FIT. When we talk about condition monitoring and reliability, the first thing we think about is things that rotate, and our minds automatically default to the bearing. But there's so many other things. And plus there's also bearings, that maybe just do this. They don't do a full rotation. So again, with that slight actuating movement, there's still going to be friction and impacting there. So we can deploy ultrasound on assets that don't do a full circle, that assets that slide, or things like couplings and gears and chain drives and belt drives, where you can't put a contact sensor, but you can still use an airborne ultrasonic microphone. So those are great options. But what we did is we categorized those hundreds of applications down into 8, what we call the 8 application pillars. And they are lubrication, which we've talked about. Then we say mechanical, which is the sliding and the rotating. Then we talk about electrical. So when you have issues with insulation material, you get surface partial discharge. The ultrasound is very good at detecting partial discharge on medium and high voltage. Could be switchgear cabinets, could be transmission distribution lines, anything in the substations, bird caging and some cabling. The 4th application pillar is steam systems. So, and mostly steam traps. And steam trap is just a valve functioning as a toilet, really. It's just collecting waste and flushing it out of the system. So our boiler feed water stays pure. So we use ultrasound to assess and diagnose the capabilities of that steam trap to keep doing what it's supposed to do, to flush the system. Valves, again, valves, if you've got any kind of a flow across a valve, you're going to have turbulence. And so we can just, put a contact probe on the valve, and we can hear whether or not the valve is blocked, if it's cavitating, if it's passing, all of those types of things. And that translates into hydraulics, which is another application pillar, hydraulic systems. So you've got flow through pipes, you've got flow through valves and diverters. Then you have, the hydraulic cylinder itself. You can have a leakage past the wiper blade on a hydraulic ram. Well, with that contact probe on the hydraulic ram, we can pick out which cylinder is leaking by, and it could just be little bubbles of oil just piddling by that seat. And then the last application pillar is what we call tightness testing. And the best example I can think of for tightness testing is in the automotive sector, where we put an ultrasound transmitter inside of the car on the assembly line, close all the doors, and then go around the doors and the windows and all of the seals, and we can determine where there could be leak points that could turn into either that bothersome wind noise or water leaks. Another place where we use tightness testing is on shipping vessels. So we can put a large ultrasound transmitter inside the hold of a ship, then we close the hatches, latch them down, and then we survey around the hatches. Now we know, and insurance companies that are insuring millions of dollars of cargo on a ship now know that if in heavy seawater, the seawater is not going to come in and destroy the cargo. So those are the 8 application pillars: leaks, electrical, lube, steam, valves, hydraulics, and tightness. Oh, I missed one. There's an 8th one.
I can't remember if you mentioned that one.
Yeah.
I mean,
I'm not sure.
So, of those, I've seen them employed to a lesser or greater degree in various plants. So, probably the most common one that I've seen is leak detection, especially on compressed air lines in manufacturing facilities. And just, everyone wants to talk sustainability these days and energy consumption. And, from my experience, air compressors and in general, compressed air is such a huge energy consumer on site. And air leak detection is usually a very, let's say, affordable way to get a very, very fast return on your investment because the amount of power loss as a result of air leaks is usually pretty high. And the other thing that kind of appeals to me about the ultrasonics as well is the capacity to do effectively like remote condition monitoring. So when we talk about the difference between, let's say, oil analysis, vibration analysis, ultrasound, oil analysis required us to go and take an oil or a grease sample. VA requires some kind of contact sensor, but with a lot of ultrasonics, you can do it at distance. And of course, there are so many environments that we experience where there's some kind of bearing and it's like way up there, or there's an airline that's inaccessible, and it's impractical to get a cherry picker out or something and access them just to do a small condition monitoring survey. But ultrasound gives you that capacity to sort of do that. I mean, for us over here in Australia, with mining being so big, conveyor bearings, that would be a really good example. Are you going to go and put a contact sensor on 100 of these things, or can you just sit in a car and have someone in the passenger seat basically just listening with a parabolic dish? So that to me, I think is the thing that just appeals most to me. But as you mentioned, that you can really go down the rabbit hole of what ultrasonics are good for.
Well, with those conveyor bearings also, because there's so many of them, it's never going to be financially practical to wire a sensor to every one of them. But like you said, if you can just point a parabolic dish, put a laser dot on each bearing, you can even pull a time waveform from like 50 meters away if you get really good at it.
Yeah, wow, that's pretty neat. So maybe as we kind of close these up, I always like to ask a question about the future, whether it's the sort of the technology or the industry. So what do you see as being like the future of ultrasound? Is there something else that's being worked on in terms of the technology and its capabilities, or is it more kind of like an awareness piece? What do you see as being sort of let's say the next 5 to 10 years of the technology?
Well, it's the industry trend is to go and try and get almost every asset that you can wired, right, or permanently mounted, and so ultrasound is really no different. You have to strike the balance between criticality and what makes sense and what doesn't make sense to wire up. But that's definitely a direction that ultrasound's going. And again, lubrication is the first pull for that technology. And we've seen it now. We've released the OnGuard product late last year, and OnGuard is just another extension of that lubrication technology that I described earlier, where we go, low level, medium level, high level. Well, the next level is having a permanent sensor mounted to a bearing, having that bearing continuously monitored, and then that signal is being continually monitored by a PLC, which then can send an impulse back to a grease cartridge and inject a microdose of grease. So what I love about that technology, that the whole concept behind that is that, first of all, we continuously know the condition of our bearing, but we actually get to lubricating bearings to the convenience of the bearing instead of the convenience of the person. And when I say that, a lot of people kind of screw their face up and say, well, what do you mean the convenience of the person? I said, well, why do we go to a bearing in the first place and pump it right full of grease? It's because we don't want to go back there tomorrow and do it again. We want to come back in 4 weeks or 6 weeks or even 6 months. And that's for the convenience of us. But for the bearing's convenience and for the bearing's health, wouldn't it be better just to microdose the amount of grease that it needs every hour or every 6 hours, depending on, and we can monitor that with the friction levels. It's kind of like when we go to the all-you-can-eat buffet and we stuff our guts out to here, and then so we don't have to eat for the rest of the day. Well, we kind of do that to our bearings and it destroys them. So this is one area where I think the technology is going. And then obviously, the big AI is the big buzzword in the market. And, if you'd asked me 3 years ago about AI, I'd say, well, AI is just a marketing tool. I just picture AI, people with their AI pepper grinder. And if you go out and grind a little bit of AI onto it, then it'll sell. Well, that's not the reality anymore. The reality now is that AI is here and it's working. And so artificial intelligence can take this data from ultrasound and start to do the diagnosis for us. And I really think that's, where are we in 5 years? Well, where are we in 5 months? Because I really think it's actually that close.
Yeah, that's interesting. And that, I guess, with AI, it is the effectiveness of it is kind of a function of the quality of the data and the frequency of the data that you collect, right? So, as long as there's a lot of good quality data, then you can do something with it on the back end. Even if the models develop over time, you can return back to the data that you've collected and get more insights out of it. And I guess, with ultrasound and being able to now do it online, now gives you that sort of that capacity, right? That really high frequency data, very high quality, and now we can sort of play with it on the back end. That's one area where, I get kind of jealous of the other condition monitoring folks, because traditional oil analysis is something where, your frequency rate is very low. People are taking samples once every 3 months, once every 6 months. And so that data density just isn't there. Now there's, a range of new inline sensors that are coming to the market and becoming more prevalent. And so I'm pretty excited to see those, but it's certainly not common. And that's us trying to move a little bit from, what you're talking about, which is I come re-grease the bearing, let's say once a week or something like that. And that's my data collection frequency versus, completely connected and online, where I'm basically getting data on a second by second basis kind of thing. So, I
mean, the word continuous can be used to our convenience, right? So, I can say that I continually monitor it every 3 months.
Yeah.
It's how you define the word continuous. Because I have a sensor mounted to a bearing, it doesn't mean I'm going to continually take data every second, because if I do that, it's going to kill the battery on my sensor. And it's data overload. You don't need to take data every second. So it's really how you define continuous.
Yeah, fascinating. Well, Allan, thanks so much for joining us. I think this was a bit of an introductory version of ultrasound, and I'm sure the audience would love to have you back for maybe like a more detailed breakdown. We can go through maybe some case studies and things like that. But no, I really appreciate your time.
I have, and we'll come back and do this, but I have a case because I talked about the complementary technologies of ultrasound and vibration, but I have a great case study that shows a complementary relationship between ultrasound and oil analysis.
Ooh, okay. Well, that's a good teaser for the next time we have you on. So we'll stand by for that. And no, really appreciate your time. And we'll look forward to having you back.
Thanks for having me. It was a lot of fun.